So this is our last section before our exam. Okay. Since we're going to be playing around with changing these states and all this stuff. Okay. If I go up this energy ladder in states from, what the heck? Right? Is that positive Q or negative Q?
Positive Q.
Positive Q. Okay. What do I call that one? Delta H with a little what? Between solid and liquid, or liquid and solid, Gloriana? Delta H with a little... It's this one. Fusion. But they just say fuss, right? How about liquid to gas, or gas to liquid, Shelby? That one is delta H.
Vaporization.
Yeah, vap. And then, Jeffrey, we've got solid to gas, or gas to solid. That is delta H with a little...
Would be the transition one?
Oh, all of them. All of them would be TRS. Yeah, that's a general way of saying all of them. But specifically, what's it called? This is how snow disappears in Minnesota.
This isn't sublimation.
Sublimation. So it'd be delta H with a little sub. Okay. So we go up the energy ladder, positive Q. Go down the energy ladder, negative Q. You have to assign these because does the temperature change during these phase transitions, Kevin?
No.
No. All right. In fact, you're at equilibrium every step of the way. Okay, so that kind of covers all that stuff. If you wanted to calculate an enthalpy, right, for one of these, or really just any enthalpy, what are its units for enthalpy, Alyssa? What are the units? See, notice how we gave you a front row spot, Kelly? What are the units for enthalpy? Now, the table's a good hint, if you can read kilojoules per mole. Okay, delta H is kilojoules per mole. So one concept here is kilojoules is just really what variable in all the stuff that we've had so far? What little symbol?
U.
Not U. Q. Q. So you really could just take a Q, divide it by the number of moles. That's a way to get enthalpy. Now realize it has to be a concept, though. Yeah, the Q has to match this process of enthalpy that we're interested in, whether that's sublimation or change in enthalpy of some process. But you could just divide Q by the number of moles. It's just like density. Density is what over what, Melissa? What's density? Density is what over what? Yeah, grams over liters or grams over milliliters, whatever, right? So if you just divide the number of grams of something by the number of mils of something, you can get density. But it has to be within the concept. I mean, it has to be that grams of that substance and the volume of that, right? It has to match. So you can always play that game with this stuff. The standard enthalpy of a reaction. Okay. That is... Why would we do that down there? Okay, I guess I'm waiting for... That's fine. Let's just do it now. H is U plus PV. So if we put little subscripts on this and deltas, we need some space here. Oh, I think, did we have the R on the, yeah, they do. They have the R on the delta. Now PV is equal to nRT. Because now we're talking about a reaction. So we want to be able, N's going to be changing now. We're going to keep we're going to keep temperature constant. So we can pull that. This is really the expression they're after. Oh, we can put the RT out front if you want. That might look better, right? Pull the RT out front. You have a little delta N. And they have, the book has a little subscript on that N. You seen it? A little G. For what? Probably, Jeff.
Gas.
Gas. It's a change in number of what molecules in this reaction? Gas molecules. So if we...
All those are N's? It's delta N's on all those?
That's a R for reaction.
Okay.
So that's the book. I'm just following what the book has. Little R for a reaction. So the standard enthalpy of a reaction. Standard change in internal energy for a reaction. Right? Oh, we want standard. We use the word standard. We should have superscript zeros in there. But if we want to calculate the change number of moles of a gas on a reaction, I don't know. You see, you've got all this stuff, but the only guy. Oh, let's say. I'm just making this up. So you can have it as complicated as you want on both sides of the equation. All you do is look for those subscripts with gas, right? So everything else can be liquid, solid, whatever. What's the change in number of moles of gas molecules for this reaction? What would delta N be? It's always final minus initial is delta. So it'd be what minus what?
3 minus 6.
It'd be 3 minus 6, so it'd be
Negative.
negative 3. That's what my delta N G would be. Negative 3 in this case. Products, sorry, final minus initial. Okay. Standard, well, stoichiometric numbers, where's that stuff? Like in this reaction I just wrote?
6 and 3.
The 6 and the 3. I don't know why they call them numbers. Stoichiometric coefficients is what we've been calling them in the past. But I think they bring it up because it's in this expression. Stoichiometric numbers, and we'll get to it, but they're in that expression. Where are they, Kevin? Stoichiometric numbers. They're the little V's there, or news. They're these guys. Right? So we'll be coming to that. So I don't know why they introduced it so early, but okay. We were talking about standard enthalpy of a reaction. Oh, I kind of skipped over something. If you're talking about, let's say we have a what was the F? Do you remember seeing this symbol? Formation, the standard enthalpy of formation of different compounds. And they're all tabulated. Like here's some right here. Okay? If we wanted to write the standard enthalpy of formation for reaction for sodium carbonate, if you want to write that standard enthalpy of formation reaction for sodium carbonate, what would it look like? Sodium carbonate would be on what side?
On the right side. Products, right?
Yeah, because it's formation, right? So you should be forming it. And then, so I put sodium carbonate over here. And then Kelly, what's on the reactant sides?
Separately?
Yeah, all those elements separately. Now they're supposed to be in their, did we save the word? They're supposed to be in their reference state, their standard states. Right? Sodium would be a solid, liquid, gas, or an ion.
Do we need to have it as a gas?
And its standard state, the solid. It's that stuff where there's a video of it. I don't know if you saw it in general chemistry. They were storing it in oil because these alkali metals, they react with water, and there's this crusty stuff on it. Take a knife, and it was kind of shiny if you cut through it. But I don't know if that helps you or not. Okay, sodium. And Kelly's right. Now carbon in its standard state. How does carbon exist in nature?
It's just carbon gas.
So carbon I think we should jump down to reference state. These are all at 1 bar. I don't know why they pick 1 bar. Everything at first has to be 1 bar if it's a gas, right? Everything at 1 bar. Now what's a bar?
Is the bar the same?
We're used to atmospheres.
Is it the same as
It's really, really close to being the same. 1 bar is 1.01325 atmospheres. So whatever. Okay. That's if it's a gas. If it's a solution, it needs to be 1 molar. Let's see. What else was there? Gas. We're kind of skipping around here. Oh, if it's a liquid or a solid, it needs to be pure. This is the things that we should be thinking of when they start talking about these reference states and these standard states. And if it's an element, it's the form that's most stable. That's kind of a weird way of defining it, I think. But once you do a bunch of these, you get used to it. So carbon is carbon solid. Oxygen, however, though, is going to be O2 with a little subscript G. Okay, now you got to balance the thing. So you could probably start with putting a what in front of the sodium? What, Kevin? 2. And then the carbon, just leave it alone probably, I guess, huh? The oxygen, you could put a... Remember the trick to doing this? Use fractions. So much easier. Put a what in front of the oxygen?
2/3.
2/3?
Or 3/2.
3/2. Right? Put a 3/2 in front of the oxygen, because now everything's nice and balanced. Okay. But is this... This doesn't look right, Alyssa. Is that the standard enthalpy of formation reaction for sodium carbonate? Since when do we have fractions in a reaction?
You just multiply everything by 2.
That's the question. Do you multiply everything by 2? You'd think you would. You'd think you would, right? But when they say standard enthalpy, this is just convention that you got to get used to. When they say standard enthalpy of formation for anything, that stoichiometric number in front of what you're talking about had better be a 1. Because if it's not, the tabulated values are off. So this has to be a 1. You do whatever you need to do to those stoichiometric numbers to make sure that standard enthalpy of formation of this compound, that's a 1.
Like that with formation? Is that the only one we have to worry about?
Yeah, well, we're not there yet. But so I think, no, there's more you got to worry about. So this has to be a 1. So that means you have to write it this way. Everybody in the world has to write it this way. Because if you multiply through by a 2, you just doubled the delta H for that reaction. Right? So the delta H's for a reaction, they depend on the reaction that you wrote. Right? Because they're all mole ratios. Right? If you remember doing this, if I had, just make this up, if this is 96 kilojoules per mole, this reaction, right? What's a mole ratio between delta H and sodium carbonate? It'd be 1 mole sodium carbonate for every 96 kilojoules, right? What would it be if you're messing with oxygen? It'd be 96 kilojoules for every
3/2 mole.
3/2 moles of oxygen, right? So the delta H corresponds to the reaction. You change the stoichiometric coefficients, you change the delta H. So that's why everyone has to write the same one. That's why we need this convention rule. It's kind of odd, but that's how it is. Okay. Maybe that's what they meant by formal equation. I'm not so sure. Okay. Standard enthalpy of combustion. Here's another one. Because Eric or somebody asked, is this the only one you got to worry about, where you need to have a 1 out in front? Now there's another one. Here it is right here. Okay. In every standard enthalpy of combustion reaction, where does they'll have what commonalities here? What needs to be in there? Forget about the compound you're burning. I'm talking about the other stuff. You need a what? Yeah, what does it let off? What does it produce? Carbon dioxide. Now, what states are important? CO2, gas. Okay. What's the other product, Shelby? H2O. Okay. But the state, Kevin, is what? This is the weird one. I always guess this wrong. You think you're burning stuff? Wouldn't you expect it to be hot? Wouldn't you expect to make H2O gas? But you don't. You want liquid. Fine. That's how it is. You just got to follow convention. Okay. What is always on the reactant side, Jeff?
Oxygen.
Oxygen. Now what state?
Gas.
Gas. Okay. So you've got all these funky stoichiometric coefficients in front of here. But whatever you're burning, pick it. This had better be a what? That had better be a 1. Okay. What's the standard enthalpy of combustion for benzene? Fine, you write it. Just this format. Okay. You produce carbon dioxide and water. And do you see how you see what's coming up? They're going to use this. You're going to have to write it, and then they're going to want to know the standard enthalpy of that reaction. They're going to want to know the standard internal energy of that reaction. So you're going to have to figure out what the delta Ng is. So that's why you got to write these things the right way.
There doesn't have to be a carbon, you said?
Yeah, whatever. That's my big
it's
X
gonna be in
here.
there, okay.
That's my big X.
Oh, that's why you said benzene.
Whatever you're burning, yeah, that will go in there. Good. Yeah, make sure you ask if I lost you here. Let's see. Make sure I kind of skipped around. I don't want to lose anything. Okay. I think we're getting most everything. We are. What if... All right, let's just practice one. Let's write the standard enthalpy of combustion for C5H12, pentane. How would you write the standard enthalpy of combustion for pentane? Pentane's a liquid, room temp.
What was the question?
Write the standard enthalpy of combustion for this compound. Standard enthalpy of combustion. Just make sure we're all on the same page here. Oh, we skipped that. Okay, we'll come back up to that. And then get the delta Ng for it. Get that delta Ng for it, what the reaction you just wrote. That's not right. It's going to be 8, right? 10 to the 16. Yeah. Then what did you get as your delta NG? I hear a -3. -3, Jeff?
Positive
Eric?
3, right?
+3.
It's final minus.
Final minus initial.
So final is 11.
Oh, but there's an L.
Oh, yeah, okay, that
It's a -3. We're doing that because that's a common mistake that you're going to have in the homework. Okay. One other thing I want to mention here. Oh, we skipped over. Well, okay. I shouldn't skip around. What if we had... Okay. And then you get delta H is some number. You have this reaction going on with the delta H. It's not in conventional format, so you want to divide through by the little stoichiometric number C. So you divide all the stoichiometric numbers by little c. What do you do to delta H? Divide it by little c again, right? Remember playing this game? What if I wanted to multiply these stoichiometric coefficients by 6? You multiply delta H by. If I flip the reaction, what happens to the sign of delta H?
Negative.
Yeah, switch the sign. Right. So that game, do you remember doing that game? That's Hess's law game, right? They give you a bunch of reactions. You know the delta H for all of them. Right? And then you got to play the canceling game. Get stuff, rearrange these reactions so that stuff all cancels, and then you get what you want. And then you add up all the delta H's and get your answer. Remember playing that game with Hess's law? Okay, so that was one way to get delta H for a reaction. That's one way to get delta H for a reaction, Hess's law. There's another way to get the delta H for a reaction. Don't forget this. You probably should have mentioned this one first. Just get Q all over the number of moles, right? If you can figure out what Q is, divide it by the number of moles that reacted, right, following the reaction, and you can get delta H that way too. And how can you get Q in a reaction? It's a C word, calorimetry. So Q is very often what times what? In this calorimetry, you need this big C. They call it the specific heat or the heat capacity or the calorimeter constant, right? Regardless, they're always big C. So multiply big C by the change in temperature and you get joules. So very often that's how you do it. But there's one, so that's one, two. A third way to get this delta H is right here for a reaction. That's a third way to get delta H for a reaction. What was this? The book wrote it in a funky way, but this is what they did. You can take any reaction, just like this guy, and if you know the, what is this called again? If you know the standard enthalpy of formation of every single compound in that reaction, you follow this expression. All you did was what, Alyssa? It's kind of messy in this equation, but what did you do? How did you get the delta H for a reaction if you knew the standard enthalpies of formation of everything? You added up all the delta H's for the products, subtracted out the delta H's for all the reactants. But you remember you had to multiply those the standard enthalpies of formation by those stoichiometric numbers. Remember doing that? So I guess that's the third way. And if you want to be technical, there's probably a fourth way, and that fourth way was right here. So all that was the homework will bring out all that stuff. So this is a real mess here. I think there's only one thing left. That's this. What if you want to know the standard enthalpy of a reaction at a different temperature? Well, you know what it is at some temperature T1. What's a better way to write this? I don't know why they did this. Delta T, right? We never write T2 minus T1. We always write delta T, but that, whatever. This is what the book wants, so this is what they did. Delta T. And then times this delta R CP0. Look how it's defined. Right? You need to add up. Now, these are in a table. These molar heat capacities at constant pressure. And sum means add up, right? But what's this symbol? You've seen it earlier. That's the what?
Stoichiometric number.
That's the stoichiometric number, right? So you have to take you have some reaction, right? Find all the stoichiometric numbers from the reaction. Multiply them by the molar heat capacities at constant pressure for that compound. What's the big J trying to do in this expression?
Just to make sure it's in joules.
I don't know why they picked big J. Look at the summation. The summation is over big J. It's just your what? In the summation, it's your little n or your little counter. And it's very, that kind of irks me when they do this kind of thing. Because we always use little i's, don't we? Right? In summations, you have little I, because then you're so used to it. Little I is 1, and little I is 2, little I is 3. But maybe that's why they picked J. Because we're not talking about 1, 2, 3, 4. We're talking about this reactant, then that reactant, then this product, then that product, right? So, and these yeah. Notice how we did, this could have been written. I don't know why they didn't do it that way. We follow the same format. We could have wrote it the sum all over J of I forgot my new J. So it's more than just a stoichiometric number. It also has to change sign. It has to be positive for products and negative for reactants. And that's what they're trying to do with this mathematically. They're trying to write little rules in a mathematical equation. So this stoichiometric number counter, it identifies the product or the reactant, but it has to be positive for, if that J compound is a product, and then that new J is not only the number in the reaction, it's also positive, right? If that little J compound is a reactant, so you're looking up the molar heat capacity at constant pressure for some reactant, yeah, you find it, and yeah, you have to multiply it by its stoichiometric number, but it's a reactant, so it's going to be a negative stoichiometric number. So that new J is kind of a complicated, ugly bugger, right? It's the stoichiometric number, but it's positive for products and negative for reactants. But we've been doing this since general chemistry, so we really don't need to make life so complicated, right? That's all we did. If you want to find the delta CP, delta anything for a reaction, right? Look it up, and it's some table, multiply by the stoichiometric coefficients, products, add them all up for the products, subtract out all the sum for the reactants. So anyway, they wanted to write an equation for us. That's why it looks kind of ugly. Okay, so let's go ahead and see if we can get through some of these. We're in 2.26. Certain liquid. Okay, so a liquid is, they give us enthalpy of vaporization. They want Q, W, change in enthalpy, change in internal energy when a half a mole is vaporized. All right, at 250 Kelvin, 750 torr. What's, I would do the easiest one first. Is there an easy one? They give us the standard enthalpy of vaporization. It's in kilojoules per mole. Sometimes units really are a good guide.
Just multiply by the number of moles to get delta H.
All right.
Or
We're on to...
divide Q by...
Hey, whoa, that thought, right? If we multiply this by the number of moles, we're going to have kilojoules. And that matches the units for delta H, matches the units for Q. It also matches the units for W. But remember, enthalpy is really what? What is enthalpy? Do you remember how it was defined? It was the heat, and had a little p subscript. The heat at constant pressure. So as this thing is vaporizing, is the pressure constant when you vaporize something? Yeah, it's just, the pressure is always what you're working against. The atmospheric pressure, the external pressure, it's constant. So your delta H here is the same as your Q, right? It's kind of how it's defined. So Eric's right on. Essentially, just take this thing times the number of moles, and that was a half, right? So that'd be 13. So my Q would be 13 kilojoules. Now, is it going to, remember, you got to put the sign on here. And that 13 kilojoules is also my delta H, right? If they wanted molar delta H, it'd be 13 kilo, right? But they just want delta H. Is this stuff positive? Let's start with Q. Is Q positive or negative? Glorianne, is Q positive or negative with what's going on here?
It's positive.
Why? You're right, but why? What's the little ladder we're supposed to write? What's on the bottom? Solid, liquid, gas. Are we going up the ladder or down the ladder? Yeah, we're going from liquid to gas, so definitely we're going up that ladder. So we better be a positive. Delta H is defined as the heat transferred under constant pressure, so it's positive, same thing, positive. Okay, so we got those two. How about work?
Negative dx delta V. Can we do that? Or do we know delta V now?
I think,
Or keep it negative and
We would need VF over VF.
yeah. Oh, there's another one. Okay.
Can we get delta U first, and then solve for the work?
If you get delta U, that's going to be that, it's a reaction, right? So you're going to have to use that, what was it? Delta NG.
RT delta N.
Yeah, well, that's one way. But all y'all also have, oh, yeah. So I don't think this one doesn't even match because it's not even it's vaporization, it's not a reaction. You're changing state, you're not changing, it's not a reaction. Okay, so let's see if we can figure one of these out. I think what helps me is when they give you this stuff, when they give you pressure and temperature, right off the bat, if you go back to general chemistry maybe, since working in a lot of those, ideal gas law. When they start giving you, what the heck? I mean, they give you the enthalpy of vaporization so you can get your Q. And then they go on and give you the, right, the temperature and the pressure. That pretty much means ideal gas law. So what we can do is, we know the pressure, right? But let's see. Let's finish this equation out. Maybe it'll make more sense. Negative P external. Delta V is what minus what? V final minus V initial. Okay, so we're vaporizing. So we're going from a what to a what? Liquid to gas. So what's the VF? The VF is the volume of the liquid or the gas?
Gas.
Gas. VI is the volume of the liquid. Okay, so you see what you're supposed to assume here? Which one's zero? Liquid. Or maybe not, the volume of liquid isn't really zero, but their difference. I mean, VL is insignificant in comparison to VG. So I guess that's a better way to say it. That VF minus VI is really just VF, because VI is so tiny. So
Yeah, we can solve for it.
you can solve for it because they give you this stuff, right? Okay. So V final is it's expanding against the 750 torrs, right?
And vaporization is expansion.
Yeah. Well, you're turning into a gas, so it has to be.
Oh, yeah.
Your volume's getting bigger. It's expanding. So this final pressure is 250. It's expanding. It ends up at 250. There's your temperature. You can calculate the volume, right, using the ideal gas law, right? So
That gives you work, and then you can get delta U with Q plus W, right? Yeah.
so we can calculate VF. What units does it need to be in though? Meters cubed. So make sure you get that. Right? So once you get it, plug it in down here. What do you put right here though? Has to be pascals. So convert what measurement to pascals? Exactly, that 750 torrs has to get converted to pascals. And then you'll have it. Okay, so that would be my W. So now that I've got the W, I've got the Q. So this is what you could do last. Get your delta U, just add them up. Okay. Now, since we're supposed to be worrying about these signs, are you going to end up with a negative sign for the W? Or is it going to be positive? If you do the math here. VF is just going to be some number, and
Positive.
it's going to, VF would be a positive number, right? Times your pascals, another positive number. You end up with a negative number. Do you want a negative number? Why? You're right. Why? Yeah. Think of it in terms of you're expanding. Is this system's the gas, is it losing energy
You're releasing it.
or is it gaining energy?
Gaining.
Like the system.
Is the system
The
releasing?
reaction is releasing.
So it's vaporizing. It's turning into a gas, right? You start with a liquid, and then it turns into a gas. The gas has to push what out of the way?
The air.
The air, the atmosphere, right? The external pressure has to push it out of the way, create organized motion in the surroundings, right? Do work on it. So does that take energy or is it given energy?
Take.
It takes energy. So the system is
Work down the surroundings.
working on the surroundings. The system is losing or gaining energy.
It's losing.
It's losing. System's losing energy, so W had better be negative. Okay? Q is positive. Right? It's
Because it gained.
It's gaining a state. It's absorbing that heat from the surroundings. Had to get it from somewhere. Okay. Does that make sense for 26? (28) Calculate the standard enthalpy of hydrogenation of one hexene to hexane. What's the chemical formula for hexane? C6H. (12?
Wait, hexane?
Hexane. C12? You sure? Remember, what was the rule for CN, H?
It's 14.
2N. Remember that? Didn't you guys do it that way?
Yeah.
Right? H2N plus 2. Remember doing this for alkanes? No? All right. So if it's an ane, it needs to be C6H14. Okay. Hexene would be C6H12. Okay. All right. Let's see. So calculate the standard enthalpy of hydrogenation. So let's see if we can. I think we need to start out with the answer. Otherwise, how do you know what the heck you're after here? How would you write this answer? How would you write that reaction? Hydrogenation of one hexene to hexane. How would you write that?
C6H12.
C6H12. On which side?
The left side.
The reactant side.
Wait, I thought, oh, 2 hexes, sorry.
What else?
And we're doing hydrogenation.
Hydrogenation.
It's not.
That's just adding what?
H2.
H2. You're just adding hydrogenation, just H2. So we'll add an H2, and you get what? Hexane. Is it balanced? It's balanced. Okay. So this is a Whose law problem.
Hess.
This is a Hess's law problem, right? You're going to have all these reactions going on here, and I don't know how many, but we're going to be adding them up, canceling stuff, get this stuff to work. We don't know what delta H is for this. If you had a table, right, you could just do this, look at the standard enthalpy of formation of products minus standard enthalpy of formation of reactants and get an answer. But that isn't what they want you to do, right? Because they give you this other stuff. So we need to use this for sure. How do you write this reaction?
C6H12.
Right.
O2 gas.
Oh, it's an enthalpy from one hexene. Yeah. Now hang on. Now, before we keep going here, should we be flipping this reaction so we don't have to erase it all, or is this written the right way?
It's written the right way.
It's written the right way because look, C6H12 is on this side. It's on this side. So we keep going, right? Kevin, what would be the rest of this? We're burning this. What would be on the product side? CO2 gas, H2O liquid.
If you were to flip it, is it just going to flip your final answer? Or would it mess up?
We're not going to get this. We're not going to get what they want.
It would be a different number.
If we did the rest of it right, it would just be delta H flipped is all.
Yeah.
Yeah. Okay, we need a balance. We're supposed to end up with a negative 4,003 here kilojoules. But we got to get this thing balanced. How do you balance this thing? 6 here, 6 there, right? 12 hydrogens, so put 6 there. 6 oxygens and 12 oxygens is 18 oxygens, right? So you get a 9. Okay. So now the rest of it, we got to get stuff to cancel. And this is what makes it a more difficult problem, is they assume that just like all these problems, you've got all these tables in the back of the book. You've got all the standard enthalpy of formation reactions known to mankind. And you have their numbers. So you can get rid of this stuff, right? You can get rid of CO2 gas. You can get rid of H2O liquid by using their standard enthalpy of formation reactions. And that's what you got to do to get rid of this stuff. Okay? Because what's missing, I guess, is the hexene. Okay? That's standard enthalpy of formation, and this must not be tabulated. It must not be in the back of the book. I don't know. But so how would you finish this? You need to get the tables, right? I don't know where my tables are. I could write the reaction, right? It would be C what and what? When you do look it up, C solid and O2 gas, right? And then you have to look up that number in the table, right? And it's going to be the standard enthalpy of formation reaction. Now there should be a, well, it is balanced, right? It'll be the standard enthalpy of formation reaction. So it's going to be written the opposite in the table, right? So you're going to have to flip the sign. And then, not only do you have to flip the sign, what do you have to do to this entire reaction?
Balance it too, so that you can cross out with the one that's
Yeah, so you have to multiply this whole thing through by, first balance it, make sure he's balanced. Well, you don't really have to, you copy the reaction in the back of the book, right? So you have to multiply this whole thing through by 6 because of right there. Oh, we're out of time. But you see what's going on here? Multiply that one times 6 too. And you don't forget to flip it. Now you got to do the same thing with the water, right? And the water needs to be on this side. Make sure you pick the H2O liquid one. And then you have hydrogen gas and half O2 gas. Look up the delta H for it.
And so this is looking at standard enthalpies of combustion.
This is standard enthalpy of formation table.
And why is the CO2 and the H2O on like the opposite side?
So they'll cancel,
Oh, okay, they cancel.
right?
That's what I was thinking. But you were just saying to flip the.
What I'm talking about flipping is when you find this reaction, the standard enthalpy of formation of CO2, right? Whatever you're forming is always on the product side. So when you find this guy in the back of the book, it's going to be carbon solid plus O2 gas makes CO2 gas. So you're going to have to flip that, find it in the table. Right?
Those are the only 3 that we use, though.
Pretty much these are the only ones you're going to care about. The rest, I bet you it's going to work out.
We don't have to.
It has to work out. If you add this stuff up and you don't get this, you messed up somewhere. So we got to finish this one. You're going to have, how many water? You need 6 of them. Well, first he's balanced. Good. Again, you look up that delta H, and make sure you look up the right one that has liquid water, not gas water. And right, you're going to have to flip the sign because it's enthalpy formation of water liquid is what's going to be in the table. So got to multiply this whole thing through by what? 6. That would be a 3. Okay. And it should work out. If it doesn't, we messed up somewhere. Okay. So give it a shot.
So we have the test on Monday. I mean on Tuesday.
Yeah, we'll work on this stuff.
On Monday, and so Monday we'll review or what?
Yeah, Monday will be review. You know, you notice we're not done yet. We're still missing another reaction. You need to get the enthalpy information of this guy in there. So you're missing a whole other reaction yet. Did you notice that? Ouch, I didn't see that. Because if we add everything up, he's not even there. So, whoops.